Question 1. Suggest the physical interpretation of dependence of Gibbs energy on the temperature. Dependence of Gibbs energy on temperature and pressure is described by this fundamental equation. In this equation, the first part tells you how Gibbs energy changes with temperature, and the second part tells you how Gibbs energy changes with pressure. If pressure is constant, then this tells you how Gibbs energy changes with temperature. And this coefficient is the derivative of Gibbs energy over temperature under constant pressure. If we plot how Gibbs energy changes with temperature, the slope is the negative s. Okay, the sign of negative means it goes down, and the slope is negative. So the Gibbs energy function of system decreases with temperature under constant pressure in proportion to the magnitude of entropy. Question number 2. Calculate the difference in molar Gibbs energy between the top and the bottom of a column of mercury in a barometer of a height of 760 mm. This question is about Gibbs energy difference of a liquid between the top and the bottom. And this difference of Gibbs energy is due to the pressure difference, because as we learned in physics, a column of liquid will have a pressure at rho g h. H is the height. Okay, rho is the density. That's the pressure of this liquid. Difference between the top and the bottom. In this case, it tells you this equals 760 millimeter mercury height. The height is 760 millimeter mercury height. So 760 millimeter mercury height pressure equals 1 atmosphere. So in other words, the difference between top and the bottom is 1 atmosphere in pressure, and that gives you a difference in Gibbs energy. As we learned in class, the Gibbs energy difference for liquid is Vm, this equation, the volume times pressure change. That's for liquid or solid. All right, so you need to know the molar volume, you need to know the pressure. Okay, the molar volume is calculated by the molar mass divided by the density. For mercury, the molar mass is 200.59 gram per mole. Density is 13.6 gram per cubic centimeter. Right? So that calculates the molar volume in cubic meter. The pressure difference is 1 bar, actually 1 atmosphere. 1 atmosphere is 1.013 times 10 to the 5th Pascal. Plug in the equation. The answer is 1.49 joule per mole. Question number 3. Suppose that 3 millimole nitrogen gas occupies 36 cubic centimeter at 300 Kelvin and expands to 60 cubic centimeter. Calculate delta S, delta G for the process. So this question is about ideal gas isothermal expansion. And we want to calculate isothermal, constant temperature. And we want to calculate the delta S and the delta G. So we know the two equations. For delta S is nR ln V2 over V1. That's isothermal expansion for ideal gas. Okay, so we know the volume change. So N is 3 millimole. You change to mole. And R volume V2 60 divided by 36, and that gives you 0.013 joule per Kelvin. So that's the entropy change. The Gibbs energy change we derived the equation for ideal gas is nRT ln P2 over P1. In this case, is the pressure ratio. Okay, but the pressure ratio can be changed to volume by Boyle's law. So this should equals to V1 over V2. Okay, and that's why you have V1 over V2 due to the Boyle's law. Okay, so plug in the volume. So volume should be V1 36, V2 60. Okay, and RT. And that gives you negative 3.8 joule. Express the molar Gibbs energy of an ideal gas in terms of pressure and temperature. So for ideal gas, we derived the equation to calculate the Gibbs energy change due to the pressure change, which is nRT ln P2 over P1. And if we set P1 to be 1 bar, or the standard state, this equation goes to Gibbs energy at any pressure. Okay, this comes to this one, equals the Gibbs energy at 1 bar, which is standard state, plus RT, or molar Gibbs energy. So let's say one more, RT ln P divided by 1 bar standard state. So that's the important equation that tells you the molar Gibbs energy ideal gas as a function of temperature and pressure. The last question, derive thermodynamic equation of the state. The partial derivative of enthalpy over pressure under constant temperature equals volume minus temperature times partial derivative of volume over temperature under constant pressure. If you remember in last chapter, we learned that enthalpy and internal energy are state functions that only depends on temperature only. And that means enthalpy should not change with pressure. This should be 0 for ideal gas. But what about non-ideal gas? So this equation addresses that issue. How enthalpy changes with pressure under constant temperature if it's not ideal gas. Okay, very general equation, this equation. How do you derive this equation? Okay, to derive this equation, we start with the fundamental equation, which tells you how enthalpy change when entropy and the pressure change. So we have 4 fundamental equations. One of them is about enthalpy change. To calculate the partial derivative, we divide by pressure change. So divided by pressure change under constant temperature, divided by pressure change, divided by pressure change. The equations are still valid if you both sides divide by pressure change. And this cancels. And so what you have is the left side is enthalpy derivative over pressure under constant temperature. The right side is temperature times entropy derivative over pressure under constant temperature plus volume. Okay, so you have this equation. And now if you compare to these 2 equations, you see the volume is already there. All right, but the partial derivative here, volume over temperature, and here is entropy over pressure, constant temperature. It looks slightly different, but if you remember, we have 4 fundamental equations. We also have 4 Maxwell relations, and one of the Maxwell relations you need to just go back to the lecture notes. One of the Maxwell relation tells you the entropy derivative over pressure under constant temperature, that's this one, equals the volume derivative over temperature under constant pressure. Okay, so this question is an application of Maxwell relations. So for Maxwell relation, and this Maxwell relation tells you the entropy derivative of pressure under constant temperature can be replaced by volume derivative of temperature under constant pressure. So by that, we have derived this equation. How do you calculate enthalpy change for non-ideal gas when pressure changes? So the good thing is, on the right side, we can measure all the variables. We can measure volume. We can measure volume change when temperature change under constant pressure. And this question tells you how important the fundamental equations and the Maxwell relations are. Okay, so that's the general equation for both ideal gas and non-ideal gas. The next question is derive this same equation but for ideal gas. So we know this should be 0 because ideal gas enthalpy shouldn't change with temperature. But now let's just apply this equation we just derived for ideal gas. Okay, let's apply this equation. So in this equation, we can calculate the partial derivative of volume over temperature for ideal gas. Okay, to do that, we start with ideal gas law, PV equals nRT. So that means volume should equals to nRT divided by P. Okay, so this derivative means the volume derivative over temperature under constant pressure. All right, so the left side should equals to the right side, also derivative over temperature under constant pressure. So under constant pressure, this is a constant. So this is a constant, this is a constant, this is a constant. So this equation seems similar to, you can write as a constant times temperature. And you want to derivative over temperature. And that is just the constant, right? The derivative temperature, that's constant. So in this case, it should be nR over P, the derivative of temperature. Okay, so just 10 nR over P. All right, so now let's plug in this into the enthalpy derivative over pressure. Okay, so enthalpy derivative over pressure should volume minus, okay, according to this equation, volume minus temperature times the partial derivative. So volume times temperature times this, the partial derivative. Okay, so why is this 0? Because ideal gas law. So PV equals nRT. So if PV equals nRT, that means volume equals nRT divided by P. And therefore this minus this goes to 0. And that is consistent with what we learned in the last chapter. For ideal gas, enthalpy should not change with pressure. It's temperature dependent only for ideal gas.